So yes, I'm not done quite grading your exams yet. I think I'll probably be able to be done by tomorrow though, so they should be back in your POs tomorrow sometime. I think with the final exam, I also, by the way, can't find an old copy of the final exam from 4 years ago either, so I think what I'm going to do for the final exam is I'm going to pick a mixture of problems from exams 1, 2, and 3, change the problems a little bit, and then I'll add some new problems, and with the new problems, I'll probably tell you what types to expect. So practicing old exam problems, making sure, especially if there are some problems that you have difficulty with, and then practicing the new types of problems that I mentioned will be the main things to focus on and studying for the final exam. Okay, so that's, and again, it's late in finals week. It's still 15 days away here. We meet today, we meet Friday. Next Monday, Wednesday, we'll take off. You can sleep in if you want, but again, I'll be available for office hours if you want to have some consultation about the project. I did, by the way, fix some things with Mathematica that were sort of not working right and they're kind of slow the other day. We'll come to those. And I'll show you what I did to fix them. Or actually, I think on this particular notebook, I didn't quite fix it, so I'll fix it right before your eyes. All right, so let's go over some things here. I'm going to go over a bunch of things that I've mentioned before, but haven't really written down on the board, so I haven't really said these real precisely. And before I do that, I would feel guilty if I didn't mention this. There's another name for analytic function. Holomorphic function means the same thing. So if you ever end up seeing something online or hearing somebody talk about complex analysis, and they're talking about holomorphic functions, and you're like, what? I know what analytic functions are, I know what harmonic functions are, what are holomorphic functions? Well, holomorphic functions are analytic functions. It's the same thing. Taylor series, Laurent series, zeros and types of singularities, and also another kind of word related to holomorphic, meromorphic functions. Okay, what are those? I haven't mentioned what those are. So let's go over this factual information. We can get it down precisely. So, again, you may or may not want to write this down. I will put it on Moodle. You might want to write some of these things down, just to help you focus if nothing else. First bullet point here, summary is, if you got a function analytic at a point, its Taylor series will converge in the neighborhood of that point, in an open disk centered at that point. And in fact, will converge to the function itself. Which you should know is not true for real infinitely differentiable functions. Again, I mentioned that example. Let's see, I think it was e to the negative 1 over x squared if x is non-zero, and 0 if x is 0. This is infinitely differentiable everywhere, including at x equals 0. Its Taylor series, however, is the 0 function. But this function only equals 0 when x equals 0. Its graph is really, really flat. You zoom in on the origin on there, it's going to look like it's a horizontal line, but it's not. It's just really, really close to being horizontal line at y equals 0. So the Taylor series approximation to this is it's a good approximation. It's the 0 function. When x is close to 0, they'll be close together. But it doesn't equal the function except at x equals 0. So there's a difference between real infinitely differentiable functions and complex infinitely differentiable functions in neighborhoods of points. The Taylor series in the complex case converges to the function on some open disk. In fact, and this came up in the test, by the way, the Taylor series will converge to f on the largest open disk centered at z0 over which f of z is analytic. On the test that came up in the fill in the blank problem, tangent of z, I said the Taylor series for that centered at 0 has a radius of convergence of blank. And this was something that I did mention before the test. Well, what's the largest open disk on which this is analytic centered at 0? It's going to be a disk of radius pi over 2 because this has got a singularity of pi over 2. So the radius of convergence of the largest open disk on which the Taylor series converges for this function centered at 0 is pi over 2. On the flip side, given a power series with a positive radius of convergence, actually you can make power series that have 0 radius of convergence. That power series has a radius of convergence of 0. What is it equal? It equals 1 plus z plus 2 factorial z squared plus 3 factorial z cubed plus 4 factorial z to the 4th, etc. This only converges at z equals 0, so it doesn't really define an analytic function. So you need to assume the radius of convergence is positive. It's going to converge to some analytic function. Moreover, on this open disk, you can differentiate and integrate term by term. And it's going to, in fact, be the Taylor series for the analytic function that it defines. You can say the AJs will equal the, if f is the analytic function that it defines, it'll equal the jth derivative of f at z0 divided by j factorial. Get the subtle distinctions between these things? Here you've got an analytic function. Its Taylor series will equal it on the biggest open disk centered at z0 on which it's analytic. And here you've got a power series. It defines, as long as it's got a positive radius of convergence, it defines an analytic function centered at z0 on some open disk centered at z0. And in fact, that power series for that function it defines is its Taylor series. Seemingly kind of subtle distinctions, but they are important. Because of these last two facts, just for your information, some authors of complex analysis books don't define analyticity at a point meaning differentiability in a neighborhood of the point. They define it as in terms of power series. They say a function f of z is analytic at z0 if it can be represented as a power series with a positive radius of convergence. From that definition and facts about power series, they would then go on to prove differentiability, and in fact, infinite differentiability. So that is the method that some authors use, and you should be aware of that. I'm not going to test you on that, but that's something you should be aware of. And actually, if you take that approach, you can think of this in terms of real analytic functions too. Though with real analytic functions, that's the next bullet point here. Real analytic functions can be defined this way as well. In other words, they can be defined as power series with positive radii of convergence. The difference is that on the real line, analyticity is not equivalent to infinite differentiability. Analyticity, having a power series representation, implies infinite differentiability, but not vice versa. You can be infinitely differentiable without having a power series representation. Power series are nice. You can calculate with them, you can approximate with them. It's good to have a power series representation of a function if you can. When f is analytic over an annulus, it's going to have a Laurent representation, Laurent series representation, which could simplify to the Taylor series representation as well, by the way. It's possible that these terms with negative powers of z minus z0 are gone. The a negative j's there could be 0. So this could be the same as the Taylor series centered at z0. But it's possible, for example, if there's a pole at z0, that you're going to have negative powers of z minus z0 in the Laurent series representation on an annulus. Annulus, again, meaning a ring shape. An inner circle and an outer circle, an inner radius and an outer radius. The coefficients we saw, if you did the reading, can be represented in terms of integrals, but we're not really too interested in that in this course. It's important for proving things, but we're more interested in an introductory course in calculations, being able to calculate the Laurent series. However, you know, calculating the Laurent series is kind of not pleasant in some ways, right? Well, it depends on your taste, I guess. I think it's kind of fun. Maybe you don't. But it would be nice, in some situations at least, to be able to calculate the order of zeros and the order of poles without calculating the Laurent series. Which brings us to the next topic to review here. Yeah, these are things that I mentioned verbally but didn't write down. They are in your book. What is a zero of an analytic function? It's a place where the function equals 0, duh, right? It's got order m, though. If you can say a bit more, if the jth derivatives of f at z0 are 0 when j is 0 through m minus 1. So, for example, just take polynomial as an example here. Z cubed plus something with higher powers here, 5z to the 4th plus 7z to the 5th has got a 0 of order what? At z equals 0, what would the order be? At z 0 equals 0. Can you tell just by looking at it and comparing with the definition here? Z equals 0 is a 0. What would its order be? F of 0 is 0. Would f prime of 0 be 0? Would f double prime of 0 be 0? Would f triple prime of 0 be 0? No. So the j equals 0 case is the function itself. By the way, the 0th derivative of a function is the function. The 0th derivative, the first derivative, and the second derivative are all 0 at z equals 0. But the third derivative, when m is 3, is not 0. There's the first derivative. There's the second derivative. And the third derivative. Hopefully I didn't make a mistake. Look good? F prime of 0 is 0. F double prime of 0 is 0. F triple prime of 0 is not 0. So the m in this case is 3. This next statement in red here is a theorem. If it's analytic at z0, it's got a 0 of order m if and only if it can be written as z minus z0 to the m power times g of z, where g is analytic at z0 and non-zero at z3. With this example, we're talking about the 0 at 0. You can factor out a z cubed. And this would play the role of g of z, and that is analytic and non-zero at 0. But this applies to non-polynomial examples as well. Did I make a mistake?
Not z to the 4th.
Thank you. We can apply these ideas to non-polynomial examples as well. Take f of z equals, let's say, z sine z. By the way, in my thinking about this right now, I'm thinking I do want to put maybe at least one problem on the final exam related to what I'm just talking about right now here. F of 0 is 0. So z equals 0 is a 0. Is f prime of 0 equal to 0? Let's see. By the product rule, f prime is going to be 1 times sine z plus z times cos z. And that means f prime of 0 is 0 plus 0 is 0. So the order of the 0 at 0 must be at least 2. Could it be 3? What's the second derivative? Derivative of sine of z is cos z. With this one, to use the product rule again. F double prime of 0 is 2, not 0. So z equals 0 is a 0 of this function of order 2. In terms of this theorem, what would the g of z be? Can I factor out a z squared into this? Well, you can if you use Taylor series. Represent sine z as its Taylor series centered at 0. You can factor a z out of that. And this would play the role of g of z then. It would be analytic, it's a power series, it's going to converge everywhere. The radius of convergence for the sine function, Taylor series, is infinity. It would be the same for this one. And it's non-zero when you plug in 0. When you plug in 0 into g, you get 1. Does g of z have another form, like maybe something related to the sine function? It does. Though you have to be careful how you write it. G of z is really, well, if z is non-zero at least, think about it. Oops. This function is going to equal that function if z is non-zero. This must be my g of z if z is non-zero. And it is. But what about if z does equal 0? You can plug 0 into that. What we have is a removable singularity is equal 0 for this function, for sine of z over z. G of z in reality is a piecewise function. It's sine of z over z if z is non-zero, and it's 1 if z equals 0. The function sine of z over z has a removable singularity at z equals 0. It does equal this Taylor series when z is non-zero. And therefore, if z is 0, if we define its value to be 1, we create an analytic function. We can, in this case, an entire function. This is analytic everywhere. And it would be another way to think of this function as z squared times an analytic function that's non-zero at z equals 0. What about singularities? Well, first of all, what's an isolated singularity? You might wonder, can there be non-isolated singularities? The answer is yes, there can be. But we focus on the simpler case of isolated singularities. You have an isolated singularity at a point if f is analytic on some punctured disk centered at the point. Notice this is 0 here. But f is not analytic at z0 itself. That's called an isolated singularity. And that would include removable singularities, by the way. If you just focus on this function as it stands without redefining it at z equals 0, as it stands, that's got a singularity, an isolated singularity at z equals 0, but it's removable. We can redefine it as z equals 0 to equal 1, and we have removed the singularity in that case. Isolated singularities come in 3 forms. removable, poles of some positive order, and the essential singularities, as we've talked about. We'll come to that. Well, that's next in this definition. Suppose F has got an isolated singularity at Z0, and suppose this is the Laurent expansion of F of Z in some punctured disk centered at Z0. Again, notice the 0 there. The inner circle is a degenerate circle, it's just a point missing. Just taking out Z0. Punctured disk centered at Z0. If the coefficients of the Laurent expansion are all 0 when J is negative, then it's a removable singularity. The Laurent expansion for sine of Z over Z is this thing, starting with the 1 there. Doesn't have any negative powers of Z there. So it's a removable singularity. It's still a singularity as equals 0 if we think of it this way, though. And in fact, these two things are equal. This and this are equal as long as Z is not 0. It's the redefinition that these two things are equal everywhere. That's the first thing. Secondly, if A sub negative M, where M is a positive integer, is non-zero for some positive integer M, but Aj is 0 for all j less than negative m, so pretend m is 5, for example. Then a negative 5, the coefficient of the negative 5th power of z minus z0 is non-zero. But then Aj is equal to 0 for all j less than negative 5. We would say z0 is a pole of order 5 in that case, in general order m. Pole of order m. And then if Aj is non-zero for an infinite number of negative values of j, then we say it's got an essential singularity. Okay, so you were tested on that. I did ask you to know about that in exam 3. But you should also be able to think of it in terms of examples too, like I mentioned, the removable singularity for this thing. Came up in the exam, finding the Laurent series for this function centered at 0 gives you infinitely many powers, negative powers of z, and therefore there's an essential singularity is equal to 0. These characterizations, these different definitions are important because they do lead to some theorems that characterize what happens noticing here, I think there's a theorem that I'm missing. Oh no, it's there, excuse me. Okay. So here's some basic facts. The book labels these as lemmas. Lemma is kind of the word for, if you don't know yet at this point, it's a word for a basic fact in math that might be useful. Maybe it's not that interesting in and of itself, but it's useful for proving something more important. If F has a removable singularity, at Z0, then it's bounded in some punctured neighborhood. Again, think of our example here, sine of Z over Z. It doesn't go to infinity as Z goes to 0. Actually, you should know this from calculus. At least if Z is real. You can use L'Hopital's rule to verify the limit of this as Z goes to 0 is 1. If you use the L'Hopital's rule, you get the limit as Z goes to 0 is cosine of 0 over 1. Cosine of Z over 1, which goes to 1 as Z goes to 0. We haven't proved that you can use L'Hopital's rule in the complex case. So don't use that, but I'm just mentioning it. It's got some finite limit as Z approaches Z0, and it can be redefined like we did with the piecewise formula as Z0. So the new function is analytic at Z0. So removable singularities, in a sense, are just sort of like they're silly singularities. Why not just get rid of it? If you got a pole of order M, then the modulus of z minus z0 to the L power, that's an L there, times f of z goes to infinity as z goes to 0 as long as L is less than m. So if you've got a pole of order 3, for example, for f of z at z0, then, for example, the modulus of this function is still going to go to infinity as z goes to z0. Poles are order 3. And then if you multiply by z0, z minus z0 to the order of the pole, again, if it's a pole of order 3, this function would have a removable singularity at z0. What's an example here? How about cosine of z over z squared sine z, which would, by the way, equal cotangent of z divided by z squared. It's got a pole at z equals 0. What's the order? It's not order 2. It's order 3. Once again, you can replace sine of z with its Taylor expansion centered at 0. You can factor out a z. Like this. And if you multiply that function by either z or z squared, and take a limit as z goes to 0, it goes to infinity in modulus. But if you multiply this by z cubed, the z cubes cancel, and you're left with something that doesn't go to infinity as z goes to 0. You can go to 1. Cosine of 0 is 1, and this goes to 1 as z goes to 0. So if you multiply this by z cubed, you get a removable singularity at z equals 0. It's the same. This is saying something, characterizing in another way. You got a pole of order m if and only if in some function neighborhood you can represent the function this way, where g is analytic at z0 and non-zero. In the case of this example, we've got a pole of order 3 at z equals 0. The g of z function in this theorem here, in this lemma, is this function here. That would be analytic at z equals 0 and non-zero there as well. Which does come back now to some of our main examples, actually, that we did. What was it? I think our main example was something like this. Maybe I had the z up top. Maybe it was a z plus 4 and the z minus 3 on the bottom. I don't remember. Doesn't matter. You don't, if you want to figure out the order of the poles at -3 and 4, by this lemma here, you don't have to actually find the Laurent expansion. The order of these poles would be 1. In the case of the pole at -3, this would be the g of z for this theorem, this lemma. In the case of the pole at z equals 4, that part would be the g of z from the lemma. If I went ahead and put a square on one of these, then the pole at -3 would have order 2 now. I'd be able to write it like that, where this part, again, is the g of z. But n is 2 in that case. So this is good news. Even though I enjoy finding the Laurent expansions, I do have my limits. It'd be nice to identify orders of poles without having to find the Laurent expansion. And this lemma justifies thinking of it in the way that I just described. If f has a 0 of order m at z0, then 1 over f of z if you prefer, has a pole of order n on z0. Conversely, if you got a pole of order n, then its reciprocal has a removable singularity there. And if you define the function, the reciprocal function, to be 0 there, then in fact it's going to be a 0 of order m. So essentially, zeros and poles of order m are kind of like reciprocal ideas of each other. There's this thing called Picard's theorem, which is pretty wild. A function with an essential singularity assumes every complex number as an output, with possibly one exception, as a value in any neighborhood of this essential singularity. So that function, e to the 1 over z, and we did look at a Mathematica picture for this. E to the 1 over z has an essential singularity at 0. If you look at the graphs of the real and imaginary parts, say they're contour maps, they're quite wild near 0. Every value except possibly one value. And in fact, in this case, the one exception is you can't get 0 as an output. Here's the definition of meromorphic. Can you see this down there? Good with the camera? A function is meromorphic over a domain if at every point of the domain is either analytic or has a pole of some order m, not an essential singularity. Then we call the function meromorphic. Rational functions are meromorphic. This would not be meromorphic. It's got an essential singularity is equal to 0. Okay, just some terminology. Probably not going to test you on that, but that's just something to know. You have heard the words holomorphic and meromorphic now. Whether they stay stored in your brain 50 years from now is another question, right? Carrie knows about brains, right? And how they store memories?
Sort of.
Sort of, okay. I don't know, maybe the electrical connections have to get used at least 10 times before it stays in there semi-permanently. I don't know. Rational functions are meromorphic over the whole thing. All right, let's come back now to the new stuff that we started talking about the other day. Residues and the residue theorem. Let's get that down more precisely. And then we'll come back to thinking about integrating 1 over 1 plus z squared. First, what is a residue? You find the residue of a function at a singularity, an isolated singularity. It could be an essential singularity, by the way. The coefficient a sub -1 of z minus z0 to the -1 power in the Laurent expansion in a punctured disk centered at z0 is called the residue of f at z0 and is denoted by the symbolism, or just res of z0 when f is understood. Theorem, you can calculate the residue at z0 without actually having to find the Laurent expansion. We've been doing it so far with Laurent expansions, but you can calculate it with this formula. Kind of an unpleasant formula to use, especially if m is very large and f of z is kind of complicated. But in simpler cases, and when m is, say, just 1 or 2, it's not too bad to use. It's actually not too hard to prove, though it's kind of unpleasant in the general case. Maybe we should look at it in a specific case where m is, say, 2. So suppose f has a pole of order m equals 2 at z equals z0, which, okay, let's just keep it as an arbitrary z0. Based on this theorem here, the claim is that the residue of f at z0, write down the statement of that theorem, what's boxed there in the case where m equals 2, would be the limit as z goes to z0, When m is 2, m minus 1 is 1, 1 factorial is 1. So we can actually just write this as a 1 or not even write it at all then. This would be the first derivative when m is 2 ddz of, here we'd have z minus z0 to the second power when m is 2. I'm not going to prove this with sentences, but the idea of the proof is just represent, first of all, f as its Laurent series and a punctured disk centered at z0. Since the pole has order 2, the most negative power of z minus z0 we're going to have is the negative 2 power. We could have a negative 1 power as well. This is its Laurent expansion in some punctured disk centered at z0. Just do the calculation, and it's pretty easy to see that the limit's got to be the residue by the definition of the residue. First, multiply this by z minus z0 squared. That's going to completely cancel. You'll be left with a negative 2. This one, you're going to get a negative 1 times z minus z0 to the first power. Then a0 times z minus z0 squared. a1 times z minus z0 to the third power, etc. And the derivative of this now can be found term by term. That's going to go away. This one's your linear term. Its derivative is going to be a negative 1, which is the residue. Plus the derivative of this thing is 2a0 z minus z0 to the first, plus 3a1 z minus z0 to the second, etc. And yeah, the limit of this as z goes to z0 is the constant term a negative 1, which is the residue. That's the definition of the residue. Why is the residue important? We've seen that when integrating a Laurent series term by term around some simple closed curve, say with the positive orientation, though we could do it with the negative orientation as well, that the only term whose integral is non-zero is the one with the negative 1 power of z minus z0. And if you're doing a positive orientation, the answer is 2 pi I times the coefficient of z minus z0 to the negative 1 power. 2 pi I times the residue of the function at z0. The residue theorem is just a little bit more general view on that. By the way, the book does mention this is sometimes called Cauchy's residue theorem, which seems unfair. Cauchy gets so much credit. Evidently, he was the one to discover all these things, so he deserves the credit, I guess you could say, but usually I just call it the residue theorem. If capital gamma is a simple closed positively oriented contour and f is analytic inside and on gamma except at the finite number of points z1 through zn, then the integral of f can be found by doing 2 pi I times the sum of the residues. Find the residue at each point, add those up, multiply it by 2 pi I, and you get your answer for the integral. Proving it, actually, once you got all these other theorems, is not that hard, really. Essentially, it amounts, at least in the picture, talking about the idea of the proof here. Say we've got 5 points where f is not analytic on and inside capital gamma. Basically, you can use the Defamation invariance theorem. Continuous deformations. You can deform this into a contour that would look like this, where you traverse each one of these circles counterclockwise, I guess they're not exactly circles, counterclockwise, before heading on to the next circle, let's see, that's not going to work, is it? Is there a way to traverse these things in the entire group of these, as well as the line segments, in such a way that the integrals on the line segments cancel because you actually traverse each line segment once in one direction and once in the other direction, but every circle gets traversed just once? Actually, I should have thought about this ahead of time. I'm not seeing offhand how to do that necessarily. In a simpler picture, it's easy. If you had just, say, two poles, you could traverse this circle once before going along this line segment in that direction, going around this circle once before coming back to where you started, if this is the starting point, by going back along this line segment in a second direction. The integrals around each of these circles definitely is 2 pi I times the residue of the function at these 2 points. And then the integrals over these line segments cancel out because you traverse them once in one direction and once in the other direction. But with this more complicated picture, I'm not quite seeing how you necessarily do that.
If you just go around halfway around the outside,
Halfway?
and go across the line segment, and then go all the way around like that.
Yeah, I think you're right. Okay. So you start right there. You're right, Kirsten. I said Kirsten. Go around halfway like that. Yeah, that works. And then you come back here, and now you actually have to reverse along the line segments. Now you have to go back this way and come around the parts you've missed before you come back to where you started. So in essence, then, you have traversed around each circle counterclockwise once, and along each line segment you've gone once in each direction. So the integrals around those cancel out. Thanks. We talked about using the residue theorem last time in integrating 1 over 1 plus z squared. Well, what did we do last time? First, we integrated this over the real line from minus infinity to infinity as an improper integral. And we saw that the answer was pi. Right? The antiderivative was arctangent. The limiting value of arctangent as x goes to plus infinity was pi over 2, and as x goes to minus infinity was minus pi over 2. I'll write x to emphasize it's a real number here. This ended up equaling pi. As a limit, you could write, the limit as b goes to infinity of arctangent of b minus the limit as a goes to minus infinity of arctangent of a. Essentially, those are the two limits that give you the answer. When you subtract them, we get pi over 2 minus negative pi over 2. And we also saw that if we integrated it around, thinking of it now as a function of a complex variable z, the poles are at plus or minus I. And if we integrate it around this pole at I, for example, we got pi. Let's double check that again with Mathematica. So here I've got the function. I'm entering its real and imaginary parts, u and v. And then these are the vector fields. We've got the vector field UV, the vector field U negative V, and the vector field VU. By the way, the reason my circle wasn't following my locator was because I made a mistake right here. I had an RE. I copied and pasted this to there without changing the RE to an IM. That needed to be changed to an IM. I do say this code below here with stream plot runs kind of slow, and it does. However, so if I move the cursor here, the circle does move with it, by the way. Let me move it to be centered here. It's running kind of slow. I clicked there, it took a few seconds to move it. However, I can make that run faster without actually getting rid of the stream plot. I mean, down here I got rid of the stream plot, but I should have thought of this. I can make this run faster by storing the graphs of the stream plots in some variables and then using those variables in the manipulate. The reason why it's running slow is it's having to recompute the stream plot every time as you move the cursor around or as you change the R. So I could do something like this. I could say stream plot phi bar. Do it like that. Stream plot phi bar is this stream plot. I'm now storing that stream plot in that variable. I could do it with the vector plots too. Vector plot copy and paste. Vector plot phi bar I could store the output of this vector plot in that variable. And I could do the same kind of things with phi star. So now I've stored these plots in these variables, and now I can use those stored names in my manipulate here, and it should run faster.
The vector plot star has a bar on top of it.
Thank you. So it should run faster because it's not having to recompute them all the time. And that's something I should have thought of, although in the midst of trying to get everything working, I didn't think of it. So now if I move the cursor, yeah, it does run faster. Okay, because it's not having to recompute. The stream plot is the main thing that slows it down. Because in computing stream plots, essentially it's solving the differential equations corresponding to the vector fields. Maybe numerically, in all likelihood numerically, so it's doing numerical routines. Essentially ND solve or ND solve value in the background without telling you. I can change the radius as well. But down further, I also added in tangent vectors and vectors from the vector field. I got rid of the stream plot in this one. But we can see as we move around the circle, the black vector is the unit tangent vector. The magenta vector is real tiny, is the vector in the vector field. It does get bigger as you head toward the singularity here. Watch, I'll move the circle closer to the singularity, and the magenta vector gets larger. Anyway, you can try to think about the positive and negative contributions to the integral here. If you're not surrounding the singularity, it turns out the integral is 0. But if you do surround the singularity, the pole at I, you get pi. And it's believable that you get something non-zero at least, because now watch the angle between the black and magenta vectors stays positive here. The entire time you move around. The angle's acute, the dot product is positive. So you get a positive integral, both for the real and imaginary part. Oh, excuse me, not for the real part I'm focused on here. The imaginary part does look like it could be 0, or close to 0. The angle is close to 90 degrees most of the time there. It's sometimes obtuse, it's sometimes acute. Is it acute ever? I'm looking at the right side now. There it's acute at the start. Slightly less than 90 degrees. Stays close to 90 degrees, sometimes obtuse. The integral along the vector field on the right is going to be 0, indicating that the final answer is a purely real number, pi. If you go around the other singularity, the real part becomes negative pi. You can see the angle between the magenta and black vectors on the left side here is always obtuse. The dot product is negative. On the right, you still get an integral of 0. The imaginary part of the integral is 0. This is the vector field u negative v, whose line integral is the real part of the complex integral. This is the vector field vu, whose integral as a line integral represents the imaginary part of the complex integral. This one ends up being negative pi. This one ends up being 0. Giving you an answer of negative pi in the long run. What I was trying to describe briefly at the very end of class last time, and still have to do it briefly today, is how to verify this answer is pi with complex integration in residues. I've got a minute extra this time, I think, so I can take a little bit more time here. Call this contour from this point to this point, say this is negative r and this is positive r. Call that contour little gamma sub r, that's what the book calls it. And then go along this semicircle up here, call that c sub r, and let capital gamma sub r be the sum of these two contours, which just means follow them in order. And then the integral, I'm not going to bother writing the function here, over the combined contour is the sum of the integrals over the individual contours. By the residue theorem, I is right there, by the residue theorem, the integral over the entire closed contour is 2 pi I times the residue. 2 pi I times the residue of f at I. I think we saw the residue was negative I pi or pi over 2 or something like that. You can calculate it with, well, it's negative I over 2, that's what we found. We get the series. You can confirm that with residue. There's a built-in Mathematica function called residue. With which you can confirm the residue is negative I over 2. At v equals I, negative I over 2. So this becomes 2 pi I times negative pi over 2, which is pi. This integral, in the limit as r goes to infinity, is essentially the same as this improper integral. I say essentially for a reason. And this integral goes to 0. Goes to 0 as r goes to infinity. And that's believable with the animation because if you look at the vector field on large circles, for example, the magenta colored arrows are really small. And they get smaller and smaller the further you go away from the origin. The book proves that this kind of thing goes to 0 as r goes to infinity. We will look at that on Friday. But because of that, in the limit as r goes to infinity, the integral of this in the limit equals pi. Why did I say essentially it's the same as this? Because if you've done the reading, you know about this. The limit of this kind of integral as r goes to infinity is called the Cauchy, or the principal value, the Cauchy principal value of this integral, which is not quite the same thing as saying this integral converges as the integral from 0 to infinity plus the integral from minus infinity to 0 if each of those things converge individually. It's not quite the same thing, and you'll see why if you do the reading. But in the case where this integral does converge, and it does converge, they will be the same thing. They're only different in situations where the improper integral doesn't converge. All right, do the reading. We'll come back and talk about that more on Friday.